In this section of chapter 21, we discuss nuclear chemistry. We're going to define what nuclear chemistry is, what kind of particles are given off in these types of reactions. Nuclear chemistry deals with nuclear reactions, radioactivity, energy production. Now, what is radioactivity? A spontaneous emission of radiation from an unstable element or atom. Now, keep in mind that emission takes place from a nucleus. Usually these are the bigger nucleus. Now, what are the different types of particles that come out during radioactivity? These are the different types of particles. When alpha particle comes out, obviously you can think that alpha particle is a fairly big one, having 2 charges and 4 mass units. So obviously this kind of big particles come out of big elements, big unstable elements. Beta emission is nothing but emission of electron from nucleus. Positron emission is positively charged electron. So you can see at the bottom number is 1, 1 is positive 1. In case of an electron is minus 1. Proton, on the other hand, has charge 1 and mass 1. Neutron has no charge, the bottom number is charge, no charge, and top number is mass. Mass is same as that of proton. This is pretty approximate because proton and neutron has slight difference in mass, but for most practical purposes would assume that their masses are the same. At the bottom we have gamma. This is nothing but like light photon. It's a highly energetic radiation. It has 0 charge and 0 mass. So you can see these numbers 0 and 0. So it has no charge and its rest mass is 0. Here we are showing you an example of a nuclear reaction and how we balance the reaction. Uranium-238. Now keep in mind that 92 that we got from periodic table, that's the atomic number or number of protons. So number 92, as long as we're dealing with uranium, we must have 92 at the bottom because that indicates number of protons. 238 is the mass. Now it gives off alpha particle, and this is alpha particle, helium-24, plus 2 charge and 4 is the mass. So how do I balance it? Just write down X before we know what element it is. So the bottom numbers needs to be balanced. 90 plus 2, that gives 92. So bottom numbers are all balanced. Similarly, top numbers need to be balanced. 234 plus 4. Let me show you with a different color. 234 is the top number, which is mass, plus 4 coming from helium, so that makes 238. So in nuclear reaction, the balancing is quite straightforward. The bottom numbers or charges need to be added on the right side, and that would be same as on the left side. Similarly, top numbers, which represent total mass, they need to be added on the right, and that would be equal to that on the left. That's how we do the balancing. Here we're going to discuss how is a nuclear reaction different from a chemical reaction. So we're giving you an example of a chemical reaction. Actually, 2 examples of chemical reaction. Carbon reacting with oxygen giving carbon dioxide. Hydrogen reacting with oxygen giving H2O. So what we see here is element in a chemical reaction doesn't get destroyed. Carbon, 1 carbon on the left, 1 carbon on the right. 2 oxygen on the left, 2 oxygen on the right. So what is the different thing that we are looking at here? Chemical state is different. Carbon on the reactant side was pure carbon. Oxygen was pure oxygen gas. But on the right side, we got a compound formed by combination of carbon and oxygen. So, and the formula of that compound is CO2. We didn't destroy any element here, nor create any element here. So in a chemical reaction, individual element remains intact, but their chemical bond could be different around it as they make different compounds. Similarly, H2O2 gives H2 plus O2 gives H2O. Again, we haven't changed identity of hydrogen or identity of oxygen. Now, next, let's pay attention to nuclear reaction. Uranium-238, when it gives up alpha, which is helium-4, it changes to thorium. Why? Because the bottom number, which represents proton, is now 90. Now, if you look at a periodic table, element number 90 is thorium. So you see here identity has changed from uranium to thorium. Similarly, in the bottom reaction, carbon-14, you know that carbon have different isotopes. This is a particular isotope that we are dealing with. Most abundant one is carbon-12. So this one is carbon-14, and that gives off beta particle, which is -10, and carbon is now changed to nitrogen because atomic number is now 7. That way you can see that it gets balanced. 7 minus 1 is 6 on the left side. So nitrogen 14 is the product, and here again identity of carbon gets changed to nitrogen as the nuclear reaction takes place. So we can now make this a statement. In a nuclear reaction, one element is changed to another element. In a chemical reaction, on the other hand, identity of an element is not changed. Now, there are different types of radioactive decay. Alpha emission is one of them. So here you see the example, uranium-238 changes to thorium. Then thorium still has extra energy, and that's what we show by an asterisk on the top. It cools off by getting rid of its extra energy, and most of the time that extra energy is given off by emitting energetic radiation. In this case, the gamma emission takes place, and that's how thorium would not have that extra energy. Beta emission, now what kind of change happens? First, assume that you have pure neutron in the nucleus. You remember nucleus is the central part of the atom, which has protons, neutrons all together, and electrons are around the nucleus. So as beta particle comes out, this is beta. Let's assume the other particle is X. Let's figure out what that particle is by simply balancing. So neutron is 0, so -1 plus 1 would make it 0. So the new particle has bottom number 1 or charge 1, and mass has to be 1 because the top numbers need to be added so that it matches with the top number of the left-hand side particle. So this is the new, this is the particle that we came up with, which has one positive charge, positive 1 charge, and unit mass. And we know that's proton. So this is proton with 1, 1. So as beta particle comes out of a nucleus, a neutron is changed to a proton. So that's pretty interesting finding. And atomic number is increased by 1, because if you increase number of protons, that means atomic number is increased. Iodine 131, as you can see that beta particle comes out, then it becomes xenon 54 because atomic number is now increased. In order to balance it, you have to have an increased atomic number or number of protons. Similarly, carbon becomes nitrogen. You don't need to memorize this, just like try to balance the bottom number, and then that should give 7 to nitrogen. Of course, it would give 7, and then you look at periodic table for atomic number 7 and you find nitrogen. Now what happens when positron comes out? Positron has a positive charge, so let's see that. Now I have proton in the nucleus. When positron comes out, of course this is unit charge, plus 1 charge, and 0 mass. Because electron has such a small mass, we approximate it to be 0. In reality, it's 1 over 1837, the mass of a proton or a neutron. So that's pretty small and for most practical purposes. So that's why we are counting mass to be 0 for electron or positron. In this case, we have positron. Now let's balance the bottom number. So that gives 0 to x, and top number is 1 because they must be added to get 1 on the top for proton. Now 0, 1. So this particle will have to be neutron. No charge and unit mass. So what we learn here is the proton is changed to a neutron and the atomic number is decreased by 1 because you are decreasing number of proton. Let's see one example. Carbon 11. When positron comes out, that's plus 1. So other element or particle will have to have 5 protons and top number has to be 11. Don't look at the top number in the periodic table because there are lots of isotopes, and periodic table only gives you average masses, so not specific isotope masses. So how we identify an element? By looking at the bottom number. That's number of protons, and which is a very characteristic feature of an element. So once you find bottom number is 5, look at periodic table and you know that atomic number 5 means boron. Electron capture. In some of the heavier nucleus like rubidium, the closest electron gets captured by the nucleus because nucleus has lots of protons. So in this case 37 protons, and electron from the orbit gets captured. It goes to the nucleus and gets captured, and that's why it's called electron capture. This mostly happens in bigger nuclei which has quite a few protons or positive charge to show big attraction for those electrons moving outside of the nucleus. So what happens when electron capture happens? Proton and electron, if you add them together, again add the bottom numbers, that gives you 0 at the bottom, 1 on the top, and 0, 1 is nothing but neutron. So proton is changed to a neutron, or number of proton is decreased in this process. Here we are showing you 3 different isotopes of oxygen. Oxygen 16, oxygen 17, oxygen 14. Again, since they're all oxygen, proton has to be the same, 8 proton, 8 proton, 8 proton. In first case, you have 8 neutrons, that makes 16, 9 neutron in second case, which is 17, and 6 neutron in third case, that gives mass 14 for the third isotope. So isotopes are really elements with same number of protons but different number of neutrons. And in nuclear chemistry, we'll be using different types of isotopes for the same element. And their properties are also quite different.